University of Chicago's own Jeff Harvey from our neighboring department of physics to give today's mathematics.
Thank you very much. I really appreciate the invitation. It's always a pleasure to come and interact with the math department. I also confess to a certain amount of terror in doing this, although I'm not quite sure what the source of it is. Maybe being a double major, realizing something much better. But anyway, I'm going to tell you about a topic that I hope has some math content that will be of interest, that has physics that you might find fascinating or interesting, independently of the mathematics. And I will try not to use physics jargon excessively and be somewhat clear about the mathematics I'm using. That's my idea. So I'm going to start out just going over some very basic things, how symmetries are used in physics. Then one of the main themes is going to be the way that quantum effects change, modify, or destroy symmetries. So I'll talk about quantum mechanics and projective representations. And then the last two parts will be about something called anomalies and something called anomaly inflow, which has played an important role in a number of recent physical developments. All right, so for the first part, as I suppose many people do in preparing a colloquium, I looked at what other people had said on various topics and went down various rabbit holes. And I came across a colloquium about the work of Emmy Noether. Why is this kind of curved? It's not minor gravitational perturbation. Anyway, a colloquium on the work of Emmy Noether. And as part of this colloquium, P. Oliver, at the Department of Minnesota, characterized modern physics as determining and allowed symmetry groups, which could be something very mundane like translational or rotational symmetry, or more exotic things like supersymmetry or E8 times E8 symmetry. Construct a variational principle with that symmetry group, compute equations of motion, invoke the work of Noether to construct conservation laws, and then try to solve the problem. Now, why do we proceed this way? Well, we proceed this way because most systems are much too complicated to solve. They involve 26 interacting electrons, non-abelian gauge theories that are strongly coupled. We just can't, tackle it head on. So we usually try to figure out and use symmetries as much as possible. And of course, we do more than solve field equations, including quantum theories. But there's an important caveat here, which was left out in this description, which is that quantum mechanics and quantum field theory often gives you symmetry structures, which are not the ones that you see classically, or not the ones that you see when you look at the Lagrangian or the Hamiltonian that you're going to vary to the equation solution. And the way that these symmetries are modified can also give you important information about the structure of the theory, the spectrum of the Hamiltonian, and I'll illustrate that with several examples. So when I say anomaly, anomaly is a word that exists in English language outside of physics and mathematics, but physicists usually mean that a quantum theory has a classical symmetry, but that symmetry is changed, modified, or destroyed quantum mechanics. Now, mathematicians have developed some of the theory of anomalies as well as they've learned how to deal with quantum field theories. So I'm thinking of work with Dan Freed, and Hopkins, Hellman, and others. And there's a nice colloquium by Dan Freed asking the question, what is an anomaly? And his answer is that the anomaly is the projectivity of a quantum theory. I will connect with that part of his definition. And then he says an anomaly is a once categorified invertible field theory. I really don't know what that means, and I won't try to explain it to you. And he says it's not necessarily connected to symmetry groups, which I think is true with the broader definition that he proposes. And being a mathematician, he looks for the broadest possible way of discussing this construction. But I will focus just on anomalies in symmetries. All right, so let's start at the beginning. One of the first things that we teach undergraduates in physics, probably sometime in their second year, I don't know, maybe the first year, I haven't taught first year physics for a long time, is that there is a very deep connection due to Noether between symmetries and conservation. The time translation leads to conservation of energy, spatial translation, for instance, conservation of momentum, rotational invariance leads to conservation of angular momentum. And for a physicist, it's a certain point that becomes so natural that you forget how wonderful it is. But again, I went down the rabbit hole a little bit of trying to understand how physicists used to think about conservation of energy. And it's as confusing as you might imagine, as confusing as it probably is to somebody fresh in physics who is told that you start with a ball on a hill and it has potential energy, and then if it rolls down the hill without friction, it has kinetic energy. But you don't actually have to solve the equations of motion to figure out the velocity. You can use conservation of energy. But why? Why is there something associated with being in a gravitational field that can be turned into something that measures the velocity? And then we learn about electromagnetic energy, thermal energy, atomic energy, all sorts of different kinds of energy. Why is the sum of these conserved, but you can convert one into the other? Without Noether's theorem telling you that it's related to time translation invariance, it's a complete mystery, and it was a complete mystery to many physicists. So this is really one of the deepest and most beautiful unifying ideas in physics, that these conservation laws are related to symmetry. Now, in somewhat more advanced physical theories, particularly in theories that involve many degrees of freedom, or quantum field theories, there's another concept where you use the symmetry of an object to understand different phases that it can be in. So the standard example of this is a ferromagnet. If you take a piece of iron, it has electrons in it with spins, and those spins carry a magnetic moment. I think actually in iron, there are little domains with groups of atoms, but microscopically, they're like little magnets. And at high temperature, the direction of those magnets will fluctuate in a random way so that the lump of iron is rotationally invariant. But as you cool it down, the lowest energy state prefers all the spins to align, and you get something that can become a permanent magnet. So all the little domains, or all the little electron spins are all pointing in the same direction. So at low temperature, the lowest energy state is a state of broken rotational symmetry, where the SO3 rotational, in 3 dimensions, the SO3 rotational invariance would be broken down to an SO2 rotational invariance about the axis picked out by the ferromagnet. What picks out this direction? Well, if you put it in a magnetic field as you cool it down, then it will align with the magnetic field. If you don't have a magnetic field that is determined in some incredibly complicated way by the exact initial conditions, all of the different orientations have exactly the same energy, but it picks one at random. And this idea of having different symmetry structures in different phases of matter extends to many different kinds of systems. So in particular, it extends to water, and is an important part of the ways of classifying states of matter that was developed by the Landau. So in water, we know that you can have a liquid phase where you have a spherical thing of water, it would look rotationally invariant. But as you cool it down, it becomes ice, at least at zero pressure. It becomes something called ice 1. Ordinary ice was ice 1, but it is. But if you put it under pressure, then ice 1 can convert to ice 2, or ice 3, or even ice 5. And for those of you that may have read Kurt Vonnegut at some point in your life, remember that ice 9 was this hypothetical form of ice that would convert all water in the world into ice 9 that was stable. There is an ice 9, but it doesn't have it. I think there's actually up to ice 15 if you expand this chart. And these different kinds of ice that exist at different temperatures and pressures are classified by having different crystallographic symmetries. The crystal structure formed by the water molecules changes as you vary the pressure and the temperature. So you can characterize the phases of ice by the crystallographic symmetry, the way that the rotational symmetry is broken down to a discrete set of rotations. Now, these different phases, this is a math, I should say, that in a finite sample of ice, these phases do not exist mathematically. Because quantum mechanically, one orientation of a ferromagnet can tunnel in quantum mechanics to a different orientation of a ferromagnet. And the rate at which it can make that transition goes to zero exponentially in the volume of the sample. For a finite sample, it's not strictly zero. So the actual quantum mechanical ground state is none of these things. But in physics, 10 to the 26 is close enough to infinity that it makes no difference, meaning the time scale for these transitions is much, much larger than the age of the universe. So these are things that exist in the thermodynamic limit of infinite volume, but in finite volume for macroscopic samples, it is also true. If you're an experimental physicist, you would never worry about this. Now, symmetry and the way that symmetries are broken for infinite systems also plays a crucial role in particle physics and is going to be connected to the discussion of anomalies. So the Lorentz group in free space at one time dimension, SO31, has a complexified Lie algebra, which is isomorphic to the direct sum of two complexified SO2 Lie algebras. And particles in physics in flat space, which are spaces to a good approximation, are classified by representations of Lorentz group. And so they are labeled by finite dimensional representations. So those are specified by a pair of half integers. And fermions correspond to the half integer choices of K1 and K2. And there are two kinds of fermions that occur in nature. One are Weyl fermions, which correspond to one of the two irreducible two-dimensional representations of the Lorentz group, psi left or psi right. The names left and right are appropriate because the parity transformation, which changes the sign of an odd number of spatial coordinates, interchanges these two copies of SU2 that live within the complexified SO3. So in parity non-invariant theories like the weak interactions, they have to be formulated in terms of these Weyl fermions, which are irreducible representation of Lorentz. On the other hand, electromagnetism and strong interactions are parity invariant theories, and one works with a reducible representation where you have both the left and right-handed component of the fermion in order to have a parity invariant.
So is this why like electrons like in chemistry are like +1/2 or -1/2 spin? Are they like are they in the Dirac case?
Well, sorry, ask the question.
In chemistry, like I remember like electrons can either be like +1/2 or -1/2 spin. Is that like are they in the Dirac case? Then it's like one of the two choices here. Or is that something else?
Well, in chemistry, one's only talking about electrons, and so it's the Dirac case. There are actually, in the Dirac case, there are actually 4 states that are described by a fermion field, which include the ordinary electron being spin up and spin down, but also the anti-electron being spin up and spin down. So in relativistic theory, it's a little bit more complicated. Both of these, if you reduce from SO31 down to SO3 and just focus on the notation, would correspond to the 2 states of the electron that you're talking about. Spin up.
Thank you.
Now, there are also what are called internal symmetry groups in physics. And the first example of this was a non-abelian SU2 symmetry called isospin that was introduced by Heisenberg in 1932. And it was based on the observation that nuclear spectra seem to be invariant if you exchange neutrons and protons. So in other words, think of the neutrons and protons as forming a two-dimensional, as transforming under a two-dimensional representation of SU2. This idea is reflected in the actual spectrum of nuclei. So here are isotopes of helium with charge 2, lithium charge 3, boron with charge 4, and beryllium with charge 5. All of them have 7 total neutrons and protons, but helium has 2 protons and 5 neutrons, while beryllium has 5 protons and 2 neutrons. And you can see that the spectra here are not exactly the same, but they're very, very similar. So Heisenberg proposed that this, you might say this just is evidence for a Z2 that exchanges neutrons and protons, actually should be an SU2 symmetry, which allows you to rotate neutrons and protons into each other, and that the strong interactions were blind to this transformation. Now, this is really old history, obviously, but in writing it, it struck me how many of the deepest ideas in particle physics have grown out of trying to understand the strong interactions, which are the hardest interactions to understand. So I just mentioned some things that have grown out of trying to understand the strong interactions. Now, the modern understanding of this isospin symmetry is a little bit different. It goes as follows. So there is a conjecture in physics which has a lot of numerical and analytic evidence for it, that non-abelian gauge theory with gauge group SC3 and with an action F is A is a connection, it's an SC3 bundle, F is the field strength, and we take this for the action, it's the coupling constant here. That the quantum field theory defined by this action, even though there is no mass parameter in this action, in its dynamics develops a mass gap, meaning that the energy of the lowest lying excitation from the vacuum is not zero. There's a gap between the vacuum and the first excited state. And lattice gauge theory gives an estimate of what that mass scale is. It's about 1600 MeV. And one of the Clay-London prizes is to prove the existence of this mass. Now, the up and down quarks, which are the quarks that bind together to make neutrons and protons, are very light compared to this mass scale. Not exactly massless, but they have mass, MC squared, which is about 1,000 times less than this kind of mass gap scale in QCD. So that means that to a very good approximation, if we were to ignore these masses, the strong interactions would be invariant under independent SU2 transformations of the left and right-handed components of the up and down quark fields. There's nothing that breaks that symmetry. The strong interactions are vector-like, meaning of the state of the left and right-handed components. And Nambu in 1960 proposed, not quite in this language, but a way that's equivalent to it, that this symmetry was spontaneously broken, just like the symmetry of ferromagnet is spontaneously broken, down to the diagonal of these two SU2s, and that is the SU2 symmetry of isospin. And this makes a prediction, because whenever you have a symmetry that's spontaneously broken, a continuous symmetry that's spontaneously broken, if you make small changes in the configuration along the broken directions, potential like this, moving this little ball along the lines of constant energy, corresponds to excitations of arbitrarily low energy. You can move it as slowly as you want along this flat direction. And so it predicts that there should be some very light particles, one for each of the broken generators of this group. And those particles are called pions. They're the pi plus, the pi minus, and the pi naught, plus minus and naught of their length. And the behavior of these pions and many of their properties and the reason why they are so light can all be understood from this idea that was proposed by Bamboo. And these pions are going to play a little bit later in the talk when I talk about anomalies and flow.
Can I just ask?
Yeah.
So this breaking is because of, like in the previous Sparrow example, we went down to a low critical temperature and then the machine broke. So where did we start where the symmetry wasn't broken, and where did we end up where the symmetry was broken? Like what was changing in which direction? And
so you could imagine going to higher temperature, like in the early universe, and then common wisdom is that the symmetry would in fact be restored. So you can imagine the process of cooling down as the cooling of the universe. There's a lot of evidence based on numerics and analytical computations that at zero temperature, the symmetry is broken. So, we don't have a parameter under our control that we can manipulate to try to unbreak the symmetry, because the temperatures required would only exist in the early universe. Too high for us to probe experiment. But we can't unbreak the symmetry. It's just broken by the vacuum dynamical effects. Yeah.
Do we have a guess for like what the Curie temperature of the universe was? Like what temperature was that where the symmetry broke?
So I think the scale would be, there's something called the pion decay constant, which I think is like 120 MeV. I would imagine that's roughly what the Curie temperature would be. You probably want me to convert that to Kelvin.
Please.
I can't do it. I don't remember. I once knew a conversion between electron volts and Kelvin, but I forgot. Okay, so this is another example. Both this and the ferromagnet are examples of symmetries that can be broken and used to classify different phases. So you can imagine a phase of QCD where chiral symmetry is not broken like this, but it would only be realized at high temperature. Now, I've given you just a few examples of symmetry in physics. There are many others that appear in information theory, string theory, conformal field theory, modular symmetries, conformal series, affine the algebra symmetries, et cetera, But the ones that I've mentioned are going to give us enough examples to talk about symmetries. All right, so now let's talk about quantum mechanics. I realize the clock at the back doesn't. Well, I just want to keep track of the time. Okay, thanks. So that I don't. This means it's between. Let's talk about quantum mechanics. So in quantum mechanics, we have a complex separable Hilbert space for a finite dimensional system. It's UAN, or if we're talking about quantum mechanics, hydrogen atom, let's say, we're looking at square integrable wave functions in R3. And there's a self-adjoint operator, the Hamiltonian, which governs the time function. Now, physical states are not associated with vectors in the space, but rather to lines in the projected space. And there is a map from projected space times itself to 0 and 1, which computes probabilities given by the absolute square of the inner product of two wave functions. And so if psi2 is a state with unit norm in pH, and I want to know the probability that a measurement, whether if it's in state psi1, which might have some characteristic energy or angular momentum or some other properties, the probability that I measure it being in state psi1 is given by the square of the sigma. So physicists would say that probabilities are invariant under changes of the phase of the wave function. And so you should think of physical states as corresponding to rays in Hilbert space. I don't know, do mathematicians talk about rays in Hilbert space, or you just say projected Hilbert space? I think rays is an old-fashioned physics term. But anyway, yeah. Well, the physical states are associated to line. Now, in simple situations, classical symmetries carry over to quantum symmetries in a straightforward way. One of the examples that we teach our students in the beginning quantum mechanics class is how to exploit rotational invariants. So you construct operators on Hilbert space, you convey the V algebra of SO3, exponentiate those to get group elements, and if you have a rotationally invariant Hamiltonian, like the Hamiltonian for the hydrogen atom, then you can decompose the wave functions into radial functions and a basis of square integrable functions on the two sphere at fixed radius, which are they're a basis for L2 of S2, which diagonalizes one of the generators, which initially chose to be rotations about the z-axis, and then omega, which is the Casimir element universal three. And you get these standard kinds of pictures that show you the spherically symmetric state of hydrogen, the first excited states corresponding to L=1, states corresponding to L=2, and physics students learn a little bit about the representation theory of SO3 by understanding how to find hydrogen atom wave functions. But there's a more complicated story. We really should be considering projective representations of symmetry groups in quantum mechanics. We have some group element G1, we map that unitary operator on Hilbert space, but in the group composition law, it's not necessary that U of G1, U of G2 is U of G1, G2, but there can be a phase because that has the same action on lines in that Hilbert space. And these phases that cannot be transformed away by a redefinition of U's are classified by group cohomology, H2 of G and U1. And for many interesting groups that appear in physics, this cohomology group is non-trivial, and you can have non-trivial projective representations. The most famous example is the central extension of SON, spin n, that for n equals 3 gives you SU2 as a double cover of SO3 and allows for spin a half particles in nature. If somehow the world was not quantum mechanical, or we didn't have this possibility of projective representations, then this kind of almost get it. Sorry, Matt. I'm out of practice doing that. Anyway, that shows would not exist. Now, here's a fancier example, which has a really kind of beautiful answer, but it's simple enough that I think I can explain everything. Some physicists in the back have seen it several times already, but it's so beautiful, I think. So physically, this is something you could realize. You take a solenoid, you make by wrapping wires around a wooden dowel like this, and then you run a current through the wires, and what happens is that there's a magnetic field inside the solenoid and no magnetic field outside the solenoid. Classically, charged particles are influenced only by the electric and magnetic fields locally, but in quantum mechanics, the holonomy of the connection is measurable. And so if you have a charged particle on a circle that exposes such a solenoid, even though it moves in a region with a magnetic field of 0, there is an influence on the dynamics, and the Hamiltonian involved not only the momentum operator, minus IV by d theta, but a periodic variable phi, which is proportional to the magnetic flux carried by the solenoid. The flux is the magnetic field times the area. So whatever the physical origin is, we can just consider this Hamiltonian. It's very simple. It has basically 1/2 p squared up to the shift by phi over 2 pi. The Hilbert space is just square root of wave functions on the circle. The eigenvectors and eigenvalues are trivial to compute. The eigenfunctions are just basis of L2 of S1, and they have energy 1/2 n minus phi over 2 pi. Yeah.
Do we see this? Like, is this like deviation from like is this effective magnetic flux on like a charged particle like experimentally verifiable, or is it too small like because you can't make it fit so
No,
much?
no, it's absolutely experimentally verified. Now, phi is a parameter that we can vary. We vary the flux. So at phi equals 0, the ground state is unique, n equals 0, and the excited states are twofold degenerate. And that's kind of completely obvious. If phi is equal to 0, n equals 0 has energy 0, and then all the other states have energy n squared over 2, and it's the same for n minus. In a generic phi, the spectrum has no degeneracy. But at phi equals pi, En is equal to E1 minus n. And what happens is that all the states are twofold degenerate, even the ground state. So in other words, the spectrum looks like this. It's a parabola, quadratic in n, and I indicated the integer points. And what we would like to understand is why this occurs, because this is very strange. Normally, when we teach quantum mechanics, we teach them that for a broad class of Hamiltonians with one-dimensional potentials, the ground state is unique. Here's a quantum mechanical system that has two ground states that are degenerate. So there's a little bit of group theory you can do. First, let's consider what happens at phi equals 0. What are the symmetries that commute with the Hamiltonian? Well, I can translate around the circle. That operator is T alpha, exponentiation of obvious P theta. And I can change the sign of theta and P theta. I'll call that parity. And at phi equals 0, translations and parity commute with the Hamiltonian. And the group that I'm getting, as you can see by just mapping these like two matrices, is isomorphic to O2. With the center of O2 being P and SO2 part being generated by T. Now, at phi equals pi, you have to modify P to get something that will commute with the Hamiltonian, and you can do this as follows. Define a unitary operator that takes psi into psi n plus 1. You can show that when you conjugate the Hamiltonian, it changes H5 to H5 plus 2 pi. And then you can check that P tilde, which is U times P, takes psi into psi minus n plus 1, which were the two states that were degenerate in energy. So we now have an operator that will pair these. And T alpha and P tilde commute with H, but if you work out, not exactly the commutator, but I guess if I multiply by the inverse on the right, I would have a relation which looks a little bit odd. It looks like the relationship between the center of O2 and the SO2 part, but with a phase in there. You can get rid of the phase by defining this T tilde alpha, and then you find this relation, which is exactly as in O2 without the tilde. But the group is not O2, because now T tilde 2 pi is minus 1. So this we thought of as a projective representation of O2, or a double cover of O2, which is known as pin group. I think the name comes with a joke, like spin. Spin without the S, because it's a double cover of O2 rather than S. Sarah made the joke. All right. So now this Hamiltonian is so simple, you might say, what's the point of this? Well, one point is that you can modify this. You can add any function which preserves this pin 2 symmetry, and the representation theory of pin 2 will still require that there be a twofold degeneracy, even though you can't necessarily solve analytically for what the energy eigenvalues are. And for example, you can add a potential which is polynomial or even cosine of 2 theta and preserve this pin 2 symmetry. And this is kind of a baby example of a much richer analysis. In fact, this comes from an appendix paper by Wygotsky and Sybry, where they use time reversal symmetry and the center of SUN symmetry to show that the strong interactions with a certain parameter which is analogous to this phi, that called theta QCD, which is part of the QCD Lagrangian. So you add to this term, which is so there's this modification of the QCD Lagrangian, which introduces this parameter, which violates time inverse symmetry. So they show that when this parameter takes the value pi, the vacuum cannot be a non-degenerate gap state. So that means in this version of QCD, where you have this new parameter and it takes the value pi, either the vacuum is no longer gapped, and this Clay millennial question is answered in the negative. There's a continuum above the ground state, or the vacuum is degenerate. There's more than one vacuum, which sounds very strange.
Does one doesn't know which is actually.
No. And I don't know whether people, I mean, in principle, I think this could be answered using lattice H theory computations, but I don't know if it does. Fairly useful result. This is probably not the real world, but it's interesting you can get this kind of non-trivial information from symmetries, which are not the classical symmetries, but are modified by quantum. All right, so let's now go back to the Pions for a minute. So I told you earlier that the lightest strongly interacting particles are these things called pions, and that they are associated to the breaking of chiral symmetry. They were first predicted to exist by UChicago in 1937, based on the idea that forces are due to particles being exchanged. So you've probably seen, Feynman diagrams where you have electron coming in, going out, it scatters off some other electron by exchanging a proton. But unlike electromagnetic interactions, which are long range, the strong interactions are short range. So Yukawa had some ways of estimating the range of nuclear interactions and said they should be done mediated by things like this, where the exchange particle here has some mass. Then you get an exponential decay in the interaction. So he predicted that these should exist, and then they were found by Perkins and Chiellini, Lattice, and Powell, going up to a mountain, maybe, and either in their airplane or at the top of the mountain, taking an emulsion, which is the same kind of emulsion that was used in old analog cameras, digital cameras, with silver iodide with emulsion. And then you can track cosmic rays through the emulsion and measure their properties and how they interact. So these were detected, and then a little bit later, they were produced in the cyclotron lab at Berkeley in 1948. And if you saw Oppenheimer, you saw pictures of the cyclotron lab at Berkeley. And the dominant decay mode of the neutral pion was the two photons, which is kind of strange because it's a neutral particle. So why does it interact electromagnetically? And Steinberger proposed that the way that it interacted was that a pion came in here, and then there was a loop of protons and neutrons that could run around here. And the photon could couple to those. The proton is electrically charged, and it would decay by this kind of loop, and he did a calculation of it. Now, the amazing thing about this calculation that he did is that he got an answer that was correct, but for the wrong reasons. And he later went on to become an experimentalist, not a theorist, and won a Nobel Prize in experimental physics. But the reason why his calculation worked was not really understood until about a decade, I guess 20 years later, in work by Adler, Bell, and Jakeen. So Adler Bell and Jaquith pointed out that the calculation that Steinberger did was not consistent with the idea that the currents, the symmetries were restored in the limit of the up and down fork nest to 0. But this SU2 left times SU right symmetry was restored. One of these papers was published in Nuovo Cimento. I guess at that time you had the abstracts both in Italian and in English. I think that's kind of marks the. So what these gentlemen discovered by doing perturbative quantum field theory calculations is that this current, which is the difference between the currents from the left and right-handed parts of these fermion fields, was not conserved, but rather had a non-zero divergence, that this effect was quantum mechanical, and it takes a very interesting form, because it involves F dual, where F is the field strength of the electromagnetic field. And this quantity F dual looks like a characteristic class for a U1 connection. So their calculation over many years was generalized to what's called the chiral anomaly. If you have Dirac fermions with both left and right-handed components, there is what you would think is a symmetry where you take the difference between the U1 symmetry acting on left and the U1 symmetry acting on the right-handed components. And you look at the divergence of that current for a general gauge theory, meaning you've got a connection on a principal G bundle on a even dimensional spin manifold, where the fermions are sections of the spinor bundle of that manifold and coupled to the gauge field, which is the connection of this G bundle. And the answer is written in terms of differential forms. That the divergence is the 2n form part of quantity, which is computed in terms of characteristic classes. These are the Pontryagin classes of the spinor bundle, and these are Chern classes of the G bundle. So this quantity on the right-hand side is the index of the Dirac operator after you integrate it over a closed manifold. And this is part of it. So there's this very beautiful connection that this anomaly in physics and symmetry, which was there classically, is not there quantum mechanically. And the way that it is violated is captured by the Atiyah-Singer index. Now, this is only part of the story, because in physics, we also have local or gauge chiral symmetries. That is, in the strong interactions or in electromagnetic interactions, the gauge symmetry acts the same on the left and right-handed components, and we can look at this divergence of this axial current, but that's not coupled to a gauge field. But in the weak interactions, we have to consider fermions that where just say the left-handed part is interacting with the gauge field. And we have to ask whether the theory is invariant under gauge transformations. So this is a problem of trying to understand the gauge invariance, what might be called an effective action, where you integrate out the fermion fields, and formally you get a quantity which is related to the determinant of the Dirac operator, or rather its magnitude. But you can show that there is a phase, and that the lack of gauge invariance can only appear projectively, that is, in the change of the phase of the effective action. And what we're interested in knowing is whether under an infinitesimal gauge transformation of the gauge field, or an infinitesimal transformation of the spin connection on the spinor bundle, whether this phase varies or not. If it doesn't vary, then our theory makes sense. It's consistent, it's gauge invariant. If it varies, then there's inconsistency. So there's an elegant way to compute the variation of this phase part of the effective action that I think was first suggested by Attia. It's mentioned in a footnote in a paper by Alvarez, Pove, and Witten on gravitational anomalies. And the answer is that you can compute an anomaly in 2n dimensions by knowing the field content, the fields that can have a complex action or chiral, and computing a certain 2n plus 2 form that is locally exact. It's D of some true Simons-like form, and then doing a gauge variation on that, and then you can show that that is also locally exact. I should have written D, it should be a D here, sorry. And then the anomaly is 2 pi times this quantity here that you get by doing this kind of descent formalism from the anomaly. So for spin-a-half fermions, the simplest case, this polynomial is simply the Dirac index density in 2n plus 2 dimensions. And you do this procedure of writing it in terms of D of a true Simons form, varying the true Simon form and writing that as D of something else in order to compute the gauge anomaly. And then you show that a bunch of physical consistency conditions are satisfied. So the very last topic, and I know that as this talk is going on, it's getting a little more technical and it'll quickly end, so don't worry, is a physical picture of this connection between the chiral anomaly in 2n plus 2 dimensions and gauge anomalies in 2n. And this goes back to some work that I did with Kurt Cowan back in 1983. And it gives a physical picture of this connection by probing quantum field theories with topological p-traps. In the simplest example, we consider a scalar field, which has a energy functional potential, which has a minimum where phi is non-zero. Phi is squared is the minimum. And then there are configurations where you have some energy density running along the z-axis, but the phase of phi varies from 0 to 2 pi as you go around the string at infinity. So in other words, phi being at the minimum of v at large distances determines a map from the circle at infinity to the circle of phases of phi. And that's characterized, obviously, by pi1 of s1, which is an integer. So there's an integer n, which characterizes these kinds of vortices or string-like solutions. And there are two complementary facts. So one is that when you look at the coupling of Dirac fermions to phi, you can show that it leads to a term in the action, which involves the phase of phi times this fourth form, the second term class of the gauge connection, which you can integrate by parts. And then a gauge variation of that leads to a term which is localized on the string. In other words, this is a little bit formal, but d squared of theta is not 0, but is rather proportional to a 2-form delta function, which localizes on the embedding of the 2-dimensional world sheet of the string into space-time. The second complementary point of view that complements this is that if you study the Dirac equation in this background, you find that there are chiral zero modes, and they have an anomaly which exactly cancels. So whatever the details, the idea here is that you can have physical systems which have certain kinds of topological interactions in the bulk. And in a system with a boundary, those interactions are not gauge invariant, but they're not gauge invariant only on the boundary. There are independent degrees of freedom on the boundary who are also lead to an anomaly, not gauge invariant, and the anomaly cancels between these two components, between the bulk and the boundary. And this kind of idea is behind many developments in mathematics and physics. So, for example, in a paper of Guy and Fried, they studied not just invariants under infinitesimal gauge transformations, but global gauge transformations, and studied gauge Dirac operators on a two-dimensional manifold and showed that the anomalies could be characterized in terms of the gauge invariant of the Dirac operator on the boundary of the boundary of X. And this is also behind the physics of quantum Hall systems, which have fascinating physics. You take electrons, you can confine them to two-dimensional surfaces in certain kinds of devices, you put a magnetic field on, and you find all sorts of fascinating behaviors. So, for example, there's a kind of conductance which is quantized, and the quantization of that can be computed in terms of Chern classes of certain E1 bundle. And the simplest action that characterizes the physics of this is simply a Chern-Simons tree form integrated over the space-time manifold of this two-dimensional surface, spatial surface. And this Chern-Simons tree form is not gauge invariant on the boundary. And that lack of gauge invariance is compensated by having zero modes in quantum Hall systems that are chiral and localized on the edge of the system. So there are both physical models and mathematical models where there are anomalies that are canceled between bulk and boundary. And it's been a very useful organizing idea. So, for example, there are recent things called topological insulators, which involve a kind of Z2 topological invariant, and more subtle applications kinds of ideas. All right, so I did not. One thing I wanted to explain when I was thinking about giving this talk was to try to explain how these anomalies in quantum field theory, which I'm afraid were a little on the technical side, but have to do with how symmetries are violated quantum mechanically, connects with the description of projective representations in quantum mechanics and how symmetries are modified there. And there is a unified mathematical framework that deals with both of these, but it relies on a fairly fancy kind of categorical description of what a quantum field theory is. And I don't have either the time or the expertise to really try to explain that. But if you're interested in the topic, then I can recommend this. There's a colloquium talk by Dan Fried and their papers by Reed Hopkins and others. All right, so I think I'm going to end here, and thank you for your attention.
Any questions?
Just kind of check some like random sample of my understanding. But so somehow is the idea in the last part you were talking about, like if given some physical phenomena is actually happening, so something is consistent. Some of these anomalies coming from the different things are kind of somehow they are forced to cancel for physical reasons. But then mathematically, it's not so obvious why that's happening, and that wasn't happening like with this kind of 2n plus 2 into 2n, or the things on the x and the boundary of x was were kind of mathematical manifestations of some cancellation that is sort of physically forced.
Yeah, I mean, the sort of mixed physics mathematics intuition that I have for this is that you start with a theory where you have the determinant of a Dirac operator, and that Dirac operator can involve scalar fields, gauge gravitational fields, and you prove that it's well defined, that it's invariant over gauge. And now, and this is supposed to be true of arbitrary choices of these background fields. Now you put on, you put this, you choose a topologically non-trivial background. It should still be consistent, but this background field kind of breaks the determinant up into two parts. One corresponding to fields which are now localized on the boundary, and the rest is the fields of the bulk. And you split it in that way, and each part is separately not gauge invariant, but because it started from the determinant of the Dirac operator that was gauge invariant, the anomalies cancel.
And so does that become a strategy for proving theorems in mathematics?
That I can't answer.
I think that's pretty good.